Okay, the YouTube is setting up. Let me see. Okay, then I will start our, I'm not sure. Okay, so then I'll start our CFSM seminar today. So that this is the kickoff meeting of our seminar series. The first speaker is Professor Xin Bian from Zhejiang University. So Professor Bian is a research professor endorsed by Zhejiang University 110th program. So he received his bachelor degree from Tongji University, China in 2006. And then he continued his master degrees and PhD degrees in Technical University of Munich, Germany. After that, he spent several years in Brown University as a postdoc, and then worked in Germany for several years, and also ETH, Switzerland for several years. So his research activity are in computational mechanics and complex fluid area. In particular, he is mostly interested on low Reynolds number multi-phase flow and rheology, cells, vesicle mechanics, and soft matter research. Okay, we will start our seminar. Xin, it's your time.
All right. Thanks, Jen. So let me know if you can see my screen fine. Full screen now? Okay, good.
Yeah.
Good. So I turn off my, let me see, how can I turn off my video? I cannot turn off my video. Okay, now it's fine. So I'm very glad to speak first in this series. So I'm also very happy that Zhen Li put together a group of people in the same field. So we organized this CFSM seminar series. I think it's a great opportunity for me and for others to share our work and to make friends also, right? So today I'm going to talk a little bit on computational aspects of bending models for lipid bilayer membranes. So it's very relevant for vesicles and red blood cell modeling. Since some of you are already doing this, so you may know what I'm talking about. And for others, if you're the first time to know the topic, I hope you can also get some idea what we are trying to do. So a particular aspect is about spontaneous curvature and area difference elasticity, which were most ignored by other people. So here we show that they are important if you want to reproduce some vesicle shapes. So I'm working now at the Institute of Fluid Engineering. So it's one part of the Zhejiang University, which is located in Hangzhou in China. So for those who never came to my university, I show a little bit geography. So here you see the big continent of China, and then across the sea you have South Korea and Japan, also Taiwan here and Hong Kong here. And Zhejiang province is south to Shanghai. So Beijing is here, Shanghai is here. And the city of Hangzhou is the capital of Zhejiang province. So the city is surrounding a beautiful lake. So if you take a picture from the corner of the lake, you can see here is the sunset. It have a lot of flowers on the river. So it's a pretty beautiful city. I hope once the pandemic goes away, you have the opportunity to visit us, especially visit me. I will be a nice host, I promise. And I want to speak a little bit about Zhejiang University itself. So it's a public university established 125 years ago. So we have over 40,000 staff. And in total, we have 60,000 students, including both undergraduates and graduates. So we have across the city 7 beautiful campuses. So I'm working in a smallest one on the bottom right corner. So in several prestigious rankings. So Zhejiang University has been always ranked in the top 100 in the last few years. In particular, it's 52 by Shanghai and QS World Ranking by 45. So we're happy to know this fact. So our university is improving all the time and trying to recruit the best talents over the world. So today, here is my outline of the talk. It's mainly divided into 5 sections besides the introduction and conclusion. So first, I will introduce 4 functionals which are used in the past to model bending elasticity, especially for lipid bilayer. And the second section, I will talk a little bit on the variation expression for the bending force. And the third section, we're going to spend most of the time here to derive and see the essential ideas how energy and force are calculated numerically, since you want to do simulation. So these are essential elements. And the fifth section, we're going to talk about results on vesicle and red blood cell. So before I start, I also first want to acknowledge my 2 collaborators, which we have been published paper in the past on this topic. The first is Dr. Sergey Litvinov, and the second is Professor Komosakos. So we were working together at ETH Zurich, and later on, I think after I left, also the lab moved to Harvard University in the last year. In the past, my work was supported by European Research Council (ERC) and also by Swiss National Science Foundation. And currently, I'm supported by National Nature Science Foundation of China. So I'm very appreciating their support here. So I want to say them in the front. Let's go ahead to do to talk about our research. So we know that red blood cell is a very important component in the mammal's blood. If you take one blood cell out of your blood vessel, so if you look at the blood, usually it has diameter of 8 microns, and the thickness is about 2 microns. So it has this typical biconcave shape. So it's very, very popular shape. So you have a disc, you have 2 cave on the other 2 sides. If you take a cut, take the membrane out, from the cross cut, you will see that membrane consists mainly 2 components. On the outside is a lipid bilayer on the outside. So it's a 2-dimensional parametric surface. So it has bending elasticity. And because of made up of lipid, it's a liquid crystal. So the area is almost incompressible. So under the lipid bilayer, you have a skeleton made up of the protein network. So it's hooked inside the lipid bilayer and give you integrity of the whole membrane structure. It's also a 2-dimensional surface, but it's different than the lipid outer layer. It has shear elasticity and stretch and compress elasticity. So when I was given this project in ETH, I was tasked to do RBC, actually, the red blood cell. But then when I studied for a while, I realized that the vesicle itself is interesting enough. So I started to do vesicle first. I want to figure out numerically how to do it nicely. So in our human life, in our body, so vesicle is also very important. For example, the 2013, the Nobel Prize in Physiology or Medicine was awarded to 3 scientists for their discoveries of machinery regulating vesicle traffic. So these people are working mainly on vesicle, of course, on the molecular genetic effects, how to control the vesicle trafficking. Anyway, so there are still a lot of mechanical properties of vesicle that are unknown, that are important to not only mechanic aspects, also to physiology. So that's motivate me to do this research. Once I have done this, I move on to include the vesicle membrane and add extra membrane skeleton, so to model red blood cell. That was my strategy. So I'm first, of course, then talked about vesicle, how we model vesicle. And if you look at a little bit molecular structure of the lipid bilayer, of course, I'm not a chemist, but I gave you a rough idea. So you have these large molecules like this on the top. You have a head with 2 tails. So it's so-called POPC here, the molecule. And these guys is so-called amphiphilic molecules. By the name, it tells you that it has a hydrophilic head and hydrophobic tail. The hydrophilic head is very attractive to water-like solutions, and the tail is afraid of water. So if you put them in a aqueous solution, they tend to formulate shell-like structure. And depending on the condition, they can form one layer structure like this by self-assembly. It's called micelle, or it can form two layers structure so that two heads are pointing both outside and inside. The tails are embedded inside, so never exposed to the water-like solution. So this is we are interested most likely in this work. It's called a vesicle. So now from the biophysical community, it's well known that we have a half-century development how we can model this lipid bilayer, especially for vesicle. So Canham, who is a Canadian mechanical engineering, was among the first to develop energy functional. So basically, he extended beam theory. If you recall your graduate school or undergraduate study, that you have one-dimensional beam. So the energy depends on the square of the curvature. So here, Canham did nothing else but to extend this philosophy into two dimensions. So in the equation 1, you see the energy is the integral of C1 squared plus C2 squared. So C1, C2 are nothing else but two principal curvatures. And KB is a constant to indicate the bending modulus, which has dimension for energy. And the integral is taken over this two-dimensional parametric surface. So he was using this functional to explain at that time why red blood cell has its biconcave shape. To some extent, he was successful. And on the other thread, Hellfish, who is a physicist, who came from background of liquid crystal, he derived independently a similar functional, so-called Hellfish functional. If you look at equation 2, it has similar structure, except that he rewrite C1, C2 as a mean curvature H, and then put under the integral. What distinguishes it from the Canham energy is that it has a reference state, which is so-called H0, or it's called spontaneous curvature. So that tells you the lipid bilayer has a preferred orientation. So that's what H0 is about. So this lipid bilayer has an intrinsic property of the material orientation. So H0 gonna indicate that kind of value. And the second integral on this equation actually is called the Gaussian curvature. But if you know a little bit differential geometry from the Gauss-Bonnet theorem, we know that if your topology doesn't change, this integral actually is a constant. For example, in the later on, we're gonna study vesicle that is almost always a sphere topology. So this energy term then for dynamics is irrelevant because it has merely added in a constant for the energy, but doesn't contribute to the force. So this is called Hellfish energy. And later on in the 80s and 90s, people realized that besides the Hellfish energy or Canham energy, which are local, depend on the local curvature, but there is an extra term. So when you bend the lipid bilayer, since it has two layers, so it has relative compressed state and extended states that add in extra energy to the previous two energy functionals. This is so-called area difference elasticity. So the energy can be expressed as the area difference. So delta A here is the area difference between the inner layer and outer layer. So from differential geometry, the area difference between the two layers can be written as an integral of the mean curvature times its 2D. This capital D is nothing else but the thickness of the lipid bilayer. So then you can tell that this energy functional now is not a local, but it has a non-local. It's a global quantity. So you have to know the whole area of the membrane to calculate this energy. So that makes it a little bit tricky to calculate numerically. Here, KAD is nothing else but merely another bending elastic modulus. And it has a similar order as KB, the original bending modulus. So D is the thickness, as already mentioned. Here, extra reference state is delta A0. Again, it tells you the preferred state of these two lipid bilayer. So now since we introduced 3 functionals, we can write the whole functional here. There's nothing more than, if you look at the equation on the top, it's nothing but EH plus EAD, so the Hellfish energy, and the EAD, the area difference energy, as this. And then the previous 3 energy functional is nothing but a specific case of this full energy functional. So here I gave the summary. So Kv is the bending elasticity with dimension of energy. H is mean curvature. It depends on the 2 principal curvature, so it's the second derivative of coordinates. And the C0 or 2H0 is called the spontaneous curvature. D is the thickness of bilayer, and so on and so forth. And note that in 80s, people also deviate a little bit from the main track. They develop a so-called bilayer couple model. The bilayer couple model is nothing else but also a special case of this full ADE model. So if you take the kappa AD to be infinity, that means you penalize the second term. So you want to have a desired error difference. If you do that, then you have the bilayer couple recovered. So here, that's the complete functional we want to model and solve numerically. To make it simpler, so we take we break down this quadratic term, open the bracket, so you can define 3 moments. So they are defined in curly font, like H0, H1, H2. H0 is nothing but a 0 moment, so it's an integral of error of 1. So it gave you the whole total area of the membrane surface. And the curly H1 is nothing but the first order integral of H. H is the mean curvature, if you recall, and so on and so forth. H2 is the second moment as the integral of the whole surface. And then if you take these 3 H0, H1, H2 into account, then you can rewrite your energy functional as a polynomial given on the bottom. So you have alpha, beta, gamma, lambda as coefficients. And these coefficients are nothing else but material properties such as kappa B and kappa AD and so on. So they are constants. And then the essential thing is how to calculate these 3 moments, right? And for people in the audience who are doing multi-phase flow, you will find the last term very familiar. So it's a lambda H0, right? H0 is nothing but surface tension energy. So we know in multi-phase flow, the surface energy should be minimized. So you have a spherical bubble or droplet, right? Okay, if you don't take into account the Maragoni effect, that your surface tension is constant, right? So this is for multi-phase flow. But the more tricky thing here is we don't only have H0, but we have H1, H1 square, and H2. Let's make it a little bit difficult to calculate numerically. So now to summarize, to model a vesicle, we have in total 4 models that are popular in the literature. Actually, the first one is the most popular one. It's also the simplest one, called a minimum model, defined by Canham functional. And the second, third, fourth are less popular. People have done very little work on this. But no matter which energy functional you are solving, you have to work together with another 2 constraints. One is the total area constraint. As I mentioned, because the lipid bilayer is in liquid crystal state, so the area is almost incompressible. So to be convenient mathematically, you want to say it's purely incompressible. You can penalize the area to make it incompressible. And also for red blood cell or vesicle, when it contains water-like liquid inside, the volume is also incompressible. So we also have to penalize the whole volume and make it as a constraint. So in total, we have 4 models. Each of them work with 2 constraints. To really evaluate our numerical scheme, so it's important to have some ground starting point. That's why we need this variational force. We can calculate the force density, so we can use software to get reference of analytical solution. Then we can compare different numerical schemes to give an estimate whose area is big or small, right? Or whether they are convergent at all. So to recall a little bit of differential geometry, I'm going over this quickly. So it's not that important. It's served as only reference. So in this basic differential geometry, you define some partial derivative by comma. Then you can define your covariant matrix tensor and contravariant matrix tensor. So covariant, you write index on the bottom, contravariant, you write on the top. And by a little bit of calculation of calculus for this differential geometry, you know the differential area is the determinant of G times two differential parameter. At the same time, you also know that the normal direction is the cross product of the two parameter. And go on, you can calculate also the Laplacian of the coordinates. So you get the mean curvature. And you take square of the curvature, then you lose the normal direction. So note the difference of equation 9. If you want to have h with the mean curvature, you have to define explicitly what is your normal vector. If you take h square, then the normal vector disappears, right? But that's make it tricky if you really want to calculate Canham energy functional, or you want to calculate other energy functional, because Canham energy doesn't have this h first order, has only h square. So you avoid to calculate n. That make the calculation simpler, right? And then we don't want to go to the derivation. So for this each curly h0, h1, h2, that you can have correspondingly the force density, also noted as f0, f1, f2 in curly notation. So for the h0, we know that is the area. So you have 2h. So you recognize this is the surface tension force, right? H is mean curvature. And then for h1 and h2 force, you also have correspondingly g, and this expression including Laplacian operator on the surface. So g is the Gaussian curvature, if you recall from a previous one. And then now you can write down really the total force density corresponding to the total energy functional. So it's given in equation 11. So this A, B, C, D, E, F, G, H, and nothing else. I don't explicitly write them down, but they are only the constants which tell you the material property, nothing else. And here we write in scalar because all the force of bending works on the normal direction along n. So n is the normal vector. So here the purpose of writing down the variational calculus is to serve as an analytical reference to evaluate our numerical scheme A, B, C, D. And also it will be served as the starting point for numerical scheme D. So we will introduce 4 numeric schemes to solve 4 physical models. So let me not confuse you. So we have 4 physical model for vesicle, and we also have 4 numeric schemes. Then in total, you can imagine there are 16 combinations, right? But we will do almost all of them. We will see later. So now we want to introduce, if we want to do simulation, we have to know how to calculate the force, not only static, but also dynamically. So we need a tool to really calculate the force and the energy, right? So the strategy is very simple. And also this strategy is taken by quite big number of scientists. So we first triangulate the surface of any topology. Here, we take a biconcave shape as an example. You can start with 20 triangles, right? You have theoretical location of a sphere for 20 triangles. And then you can always divide your triangle into further 4 pieces, right? So you have refined your mesh on the surface from 20 to 80 to 320, and then 1,280 and 5,120 and so on and so forth, always by 4 times, right? And then based on the neighboring triangles here, for example, in the middle, based on 2 triangles, you can define the quantities you want, like area, a mean curvature, and so on. You can also define this quantity based on a larger stencil, which involves 6 neighboring triangles. So that will differentiate the 4 schemes I'm going to present next. So the first scheme is called numerical scheme A, was very popular actually. Some of the audience are still using it. It started from Cantor, so who was a student of Nielsen from Harvard Physics. So they were using this scheme to do polymer network in the first place in the 80s. So the idea is very simple. given two neighboring triangle, you can draw two normal vectors, n1 and n2, and these two normal vectors form an angle called theta e. Then you take a cosine theta, and then subtract it by 1. So you can imagine when the theta gets bigger, this energy gets stronger, right? Get bigger. And then you have a constant in the front. It's called a kappa b tilted. I make a kappa b tilted because it's not exactly as kappa b we saw in the early slides. So the nice thing of this formula is numerically it's very simple to calculate and to understand its motive, but it has no correspondence to the continuum functional we just saw. There's no correspondence between E here, the discrete energy, and the mean curvature H or A. There's no correspondence. And the K kappa B delta has no unique relation with kappa B. So you have to somehow rescale it. And then if you introduce a reference state theta 0, has also no clear correspondence to H0, which is from the continuum mechanics functional. But okay, this functional is not completely useless. It's okay if you write your differential geometry in Mond form. That means you have a relative flat surface. So this equation 12 is relative okay. But if you go to an arbitrary shaped, you will see later that it's not accurate and it doesn't converge sometimes. But it was popular and because it's simple. So the pioneers of red blood cell people from Kanyadakis group, like Pivikin, Fedosov, or other people, Krieger, they all use this formula. So Krieger even make a simpler approximation of this. If you take a Taylor expansion of this cosine, you get a second expression, which is theta e minus theta 0 squared. So it's nothing else but even a simpler form of the first one. So it's first order Taylor expansion, right? But they are the same class. So the second scheme, actually, conceptually, I like it very much. It's as simple as the first one, but it has all the properties nicely. I will present later. So I want to explain how it works. So imagine you have two shadowed triangles that are also neighbored. These two triangles are your real triangles of your surface. Then you imagine outside of your surface, you create two parallel dashed triangle. So it has distance from the original shadowed triangle h. So the distance is h in perpendicular direction. So then the two dashed triangle with two shadowed, the real triangle, formed a portion of cylinder, right? You can imagine. And this portion of cylinder is characterized by a theta e, which is nothing else but also the angle between the two normal directions, actually, the same as the scheme A. And now if you imagine all the curvature remains nothing else but on the cylinder. So then you can define the first moment of the curvature. That means on the axis direction, your curvature is 0 because it's a line. And on the cross direction, along the circumference, you have radius 1 over h, the curvature for radius h. And then if you times the area, which is h, theta e, and area e, so you define the first moment. Recall the first moment is the mean curvature times area. And then the h, the small h will cancel out. So in the end, you have 1/2 RE and theta e. So RE is the length of the cylinder. Theta e is the angle between the two normal direction of the triangle. You see, it's very, very subtle and very coincident. It's also the nice property of this method, actually. Imagine if you define, instead of the first moment, you define h0, then the h, this small arbitrary parameter h, will not disappear. If you define h2, which is the second moment, the h also doesn't disappear. So which make the scheme inconsistent. But only when you define the first moment, h never appear in the end. So that's the beauty of this method. So now you know the first moment on this local point, right? Then you know also from triangle, you know each triangle's area, and then each triangle contribute to the index 1/3 of its area. Then you know exactly each index local area. Then you use the first moment divided by your local area, you get mean curvature. You see, that's the very simple formula. So as simple as the scheme A, but you don't define curvature directly. You define first the moment and then divided by area, then you get the mean curvature. Then once you have the area AI in discrete and H1, HI in discrete, you have everything. So that's the how it works. And the scheme C is also very popular, especially by Gomper from Jülich. So this one goes in a hardcore way. So basically, you have to define the Laplacian operator on this triangular network. So long story short, it uses 6 neighbors, and for each edge, you have to use 2 opposite angle phi k and phi l to take their cotangent value. And for any arbitrary w function, the Laplacian is given as formula 14. So this cotangent sum times the difference between the two function values and index I and j divided by the Bernoulli area. So the Bernoulli area is a typical standard definition for index I. So it's a closed area, so which is shadowed here. This also can be expressed as a cotangent function here. And then once you know the Laplacian operator of W, you can change W to arbitrary function, for example, the coordinate x, right? Then you can use this to get your mean curvature squared. But then you know that we are missing still n, the normal direction. So that's come into play the scheme D. The scheme D is very similar to scheme C in every aspect, except how we're gonna calculate the force. So I will explain later how scheme D and C are different. So for now, how they calculate Laplacian, how can they calculate H, and how they calculate energy are exactly the same. But to calculate the force, scheme C and scheme D are different. And for scheme A, B, C, D, you know, in A, we don't have explicitly Canham energy directly defined. We only define energy directly, so we don't define H or A. But for B, C, D scheme, we define H and A discretely. So we can define the 3 moments discretely, easily, right? Then we can calculate the discrete energy like this, 21. And then if you take Newtonian mechanics, you know the discrete energy, you take a partial derivative with coordinates, then you get force directly. That's how scheme A, B, C are getting their forces by formula 22. So it's very direct. But only scheme D is different. How? Let's take a look. So scheme D, when it calculates energy, is the same as scheme C. But when it calculates force, it has to use the variational formula. Recall that we introduced the variational formula to get the force density, which is given here. I repeat it here as 23. So the force density are expressed in geometrical functions like h, g, and Laplacian. So the difference now here come into play that when we calculate the force, we also use 23 and then use the geometric function again. And then we are missing g undefined. So we have to introduce the Gaussian curvature in discrete form, which is given in 25. And also the normal direction in the index is given as a weighted sum of the neighboring triangles normal direction, weighted by the incident angle, phi. Recall phi is just the 6 angles around the center index I. So in this way, we calculate the force. So we need to rely on the variational force density expression to calculate the force for scheme D. Let's make it different. So to summarize, so we have this four scheme ABC. So A doesn't have definition of H, G, or H0 or AD, nothing. But because the force is calculated by Newtonian mechanics, taking direct derivative of the discrete energy, so it conserves linear momentum, right? That's very clear. Also, scheme B, C are doing the same. They all conserve linear momentum. But B, C has advantage because they define H directly, but they don't need to use G, so they don't define G. But they also can introduce H0 and the error difference elasticity. So they can solve all the 4 models we introduced early. And scheme D, it defines all these 4 quantities, H, capital H, G, and H0 and ADE. But because the force is not taken from the direct derivative of the discrete energy. It relies on the force density from the variational formula. Of course, you cannot expect that it conserves momentum, but that's the down part of scheme D compared to scheme C. Besides this, they are all very similar. So before this work, people have done a lot of work using ABCD to solve Canham energy, but surprisingly, nobody extend this scheme to solve the second, third, and fourth vesicle models. So that's gonna be the task of this work. So we first take a look at some analytical value. So if you are given a sphere, then we know exactly the Canham energy for the sphere, right? It's 8 pi. So let's calculate on triangles who are doing better, who converge fast. Then on the x-axis, given the number of triangles, to the right are going to be increasing the number of triangles, right? And you see that all of them eventually converge given enough number of triangles. But scheme A, which is the simplest, doesn't give you the correct number. But of course, people may argue that we can rescale the constant to make it converge to the correct one, 8 pi. But look at the second figure. Now we are calculating the same energy, not for a sphere now, but for a biconcave shape. So the biconcave shape is taken from the red blood cell community. Given the exact shape, we can also use software like MIPO or Maxima to calculate analytically. So the value is around 48. So you see scheme A also converts, but converts to a wrong value. You see the wrong value, the scaling is different between the biconcave and the sphere. So you can get a sense that scheme A will converge, but for different shape, it converts to different value. And then it's pointless to rescale it because you don't know which constant to rescale for. And now going further, we want to test whether they are doing well for Hellfish energy and AD energy, which are important for the second, third, and fourth model, right? Again, we are taking sphere and biconcave shape as a target. And you see that scheme A is out of the picture because you cannot extend scheme A to do Hellfish or ADE. It doesn't have definition of H, right? Therefore, we only show scheme BCD. And you always see the circles, which are for scheme B. They always converge a little bit faster or earlier with smaller number of triangles. But eventually, they all go to the correct value. So now let's do something more challenging to look at the shapes of vesicle at equilibrium. So I want to explain a little bit the procedure. So how do we get the shapes of a vesicle? So basically, you get the energy and then you get the force. The shape gonna be driven dynamically by force. And meanwhile, you constrain the area and volume of your vesicle. And use leapfrog integration to have time reversibility. And then you introduce some viscous damping, so you can remove the kinetic energy when you do this minimization thing. And also we add DPD-like white noise to explore the energy landscape, so we can find the minimum value of your energy at equilibrium. Of course, on the way, we regularize the triangle, but these are very technical, so we don't want to waste your time to go details. But the initial configuration is important. We start from various of initial configurations, so we can really try to explore all the possibility on the energy landscape. When we take among the multiple local minimum, the minimum one, so you get the global minimum. For example, now we do the minimum model for the Canham energy. So people have solved this from physics, right? Because you always have this simpler functional, which is h squared. So you can solve using axisymmetric ODEs. This was solved by, for example, Zeffert from Stuttgart, and also all his collaborators. The thing we are doing is doing three-dimensional, but to validate our code. So you get this complicated phase diagram. On the y-axis, you have the energy normalized by the sphere, which is non-dimensional. On the x-axis, you have the volume, which is reduced volume. So the reduced volume is defined as the vesicle's volume divided by the sphere's volume. The sphere has exactly the same area as your vesicle. Therefore, the sphere has the biggest volume. So your reduced volume is always smaller than 1. So you have some bifurcation and so on and so forth. So when you have a smaller reduced volume, we have very nice, interesting one sphere inside another sphere. It's also called stomatocyte. So it's very challenging to reproduce this. So, but all the schemes B, C, D are able to reproduce. I will show you details later. So on top right is the rendered figure that using scheme B to reproduce this one sphere embedding another sphere. So it's still a spherical topology because the two spheres are connected with a very narrow neck. So it's almost budding, but it doesn't happen yet. And to be coincident that this iPhone, they have wallpaper has exactly the same inspiration from our simulation. I don't know is it a coincidence, but I was laughing at them. And later on, if you look at the convergence, because I take out and zoom in this more interesting area of reduced volume is more relevant for red blood cell around 606, right? So you see scheme B, when you have 1000 triangles, it's already on the line of the target. When you make it 4 times, 5000, it's still on here. But scheme C and D has very, very big difference when you change the resolution. Only 5000 triangles are enough. So to give you a taste, scheme C and D are more expensive in dynamic simulations. So here are more details for Canham energy. So I list on the first column is A, B, C, D, 4 schemes, and I compare the shapes for different reduced volume they produce. If the reduced volume is about 0.65, you see scheme A is also able to reproduce this prolate or cylinder-like shape. But once it comes to smaller reduced volume around the biconcave shape, it doesn't produce biconcave actually. But people reported the scheme A that has biconcave shape only because they have introduced also the skeleton, which contribute to change the shape. But the lipid bilayer itself by scheme A doesn't reproduce actually the biconcave, but scheme VCD actually does this nicely, and they coincide with each other's result. And then if you go down, the reduced volume is more challenging. So you can tell that scheme B is always perform better, has no, for scheme C, if your resolution is small, it generates this crossed shape, which is non-physical, right? It also has generated these dumbbells, which is also unphysical. But scheme B is always consistent with other results from literature, even though it has very, very small resolution of 1000 triangles. And then if you take a further of Hellfish energy, which has this spontaneous curvature, for example, say 0 equal to 2.4 in the non-dimensional units. So BCD can generate, in particular for this middle column, a vesiculation. That means you have very narrow neck. It's almost cutted, but still connected. And if you have another parameter with say 0 to equal to 3, this is almost cutted. So for scheme B, only with 2 triangles, it's very stable. I was very surprised. It stays there forever. It doesn't break. But for scheme C and D, if you give this challenging task, it can run for moderate case. But if you have this very, very narrow neck, which is almost budding happening, that it breaks down. So later on, we extend this model to solve the full functional, which is so-called bilayer couple model. Now you have 2-dimensional diagram of the phase. So on X, so for the Y-axis, it's still the reduced volume. For X-axis, now is the reference bending state. So now the difference is when you introduce spontaneous curvature, your shape at the equilibrium of the vesicle are still axisymmetric. Only when you introduce this area difference elasticity, your shape become non-axisymmetric. That's the interesting thing. So the spontaneous curvature only gave you those budding and vesiculation, which Canham cannot do. But the ADE model or bilayer couple model gave you not only the budding and vesiculation shape, also gave you the non-axisymmetric shape, which are all observed experimentally. On the right here is by Japanese group on soft matter. Also, a few years back, Xue Jin, my friend and colleague, also used DPD to reproduce the bilayer couple model, which has also very nice feature. So, okay, my time is short. I want to say briefly about my perspective, like how I'm working on now, what I'm working on. So given this long road, after I model to my standard, I like it. I how to say, I like the result. So I move on to introduce on top of this lipid bilayer energy functional, extra membrane skeleton energy functional, which is a string hardening energy. So given here, so you have alpha, beta, but they are nothing else but a function of local principal stretches here. So this is following most likely the work of Lim on Pinas 2002. And then introduce two modulus, it's K alpha and mu, which defines the stretching and shear strength. And then you have four nonlinear terms which are needed to calibrate. So now you have the complete model of RBC, which is also the most general one, leaving out the uncalibrated parameters. Together with the stress-free shape of membrane skeleton, we can calibrate together. So long story short, we can know in the end that the stress-free shape from a membrane skeleton is almost like oblate, but it's not oblate because this oblate-like shape, we have to get it by minimization of vesicle. Actually, that's also exactly what Lim does. And in the literature, people take this oblate-like for their stress-free shape of membrane skeleton, but they take it for the wrong reason. Why? Because only taking this shape, we can really reproduce the equilibrium shape of RBC in different physiology state. Here you see the famous sequence of stomatocyte, discocyte, echinocyte. So in the middle, which are the most popular shape of discocyte. One is top view, the other is side view. But if you change the bending reference state, actually to the right, you have three states of echinocyte. Of course, you can go further, then they may break down. So it's irreversible. Then we don't go there. To the left, you also have stomatocyte by changing the reference state to the other direction. So this is the parameter essentially relate the mechanics with physiology, such as pH value of the surrounding, right? And this SDE sequence has been observed, given here as example from Bessie's book, the image of RBC for these 7 shapes. So you can find really one-to-one correspondence. And given this model with the lipid bilayer as outside and the membrane skeleton in the inside, you can couple in Stokes flow, right? With the classic boundary integral method. Since you already have the mesh, why not use it? And then you can solve all the velocity field on the mesh. And this is very classical. I think many of you may already know. So you have the far field, background field, could be a shear flow or Poiseuille flow. And then you have this second tensor, which is called Stokeslet. And you have the third order tensor, Stresslet. And the Stresslet is important when you have viscosity inside and outside of membrane are different. So the lambda characterizes the ratio between the inner outer viscosity. And then you can solve the Stokes flow by changing the volume integral to a surface integral, right? That's why it's called boundary integral. And then you can put the RBC or vesicle however you want in the shear flow, for example, right? We can observe all these fancy shapes of different tumbling tank treading morphology as already reported in the literature. So this is on progress. So I don't want to talk about more. I gave you a taste what we have been working on. So my time is short. Now to summarize, I show a phase diagrams for minimum model, spontaneous curves model, and bilayer couple model, and ADE models. So we didn't show explicitly ADE model because ADE model is used usually in dynamic. It's a subset for the phase diagram of bilayer couple model. So we have evaluated 4 numeric schemes. To conclude, scheme B, the area aspect is superior, conceptually simple, computationally inexpensive, and it converges faster with smaller resolution, and it's very stable for vasculation budding. And with this ADE model for the lipid bilayer, together with the membrane skeleton model, we can regenerate the SDE sequence, stomatocyte, discocyte, echinocyte. Thanks for your attention.
Okay, thanks, Chin. It's very rigorous work to model the the bending and the geometry and topology of the vessel lipid bilayer structures. So we have about 10 minutes Q&A time, and if we have question from the audience, you can unmute yourself and ask a question to Dr. Bian. So any question?
Oh, hi, Xin. This is Jiaoyan again.
Hi, hi.
Yeah,
Go ahead.
thank you. Yes, thank you very much for the very nice and very kind of clear review on the models and the scheme. So in fact, I just have a question about the force calculation. So seems here you kind of present a various, maybe 4 types of models to describe the bending behavior of the vesicle. So I'm just wondering, when you do the force calculation, I mean, in the dynamics, like the movie showing the dynamics of the structure. So for your force calculation, so based on your different model, like the 4 maybe models, then do you compute the force like numerically, or you have the analytical like expression?
We have to compute the numerically, of course. So if you already know the discrete energy, right, which is defined on each vertex of the triangle, then you already can take a partial derivative, which is a little bit tedious but simple, to take the partial derivative with the coordinate of your triangle. Then you get force directly. So it's very straightforward, but a little bit tedious.
Oh, I see.
So it's all dynamic. So you can directly put this model, although we show you the phase diagram at the equilibrium, but you can put this model directly in flow, which is dynamic, because we have all the forces. So the minimization process, actually, we are not doing Monte Carlo, actually. We are doing driving by force, the minimization, like gravity, you know the potential, then you know the force. So,
yeah, basically,
so it's a dynamic, although the time is irrelevant, right? This dynamic has no real time. It's a mathematical time, so to say.
Yeah. So basically, the governing equation is just the Newton's second law, right? With the forcing
forces, yes. Once you know the energy, the force is straightforward.
I see. Yeah, thank you very much.
And for scheme D, it's a little bit different, because as I mentioned, maybe I was too fast. Scheme D for energy is the same as the other. You calculate discrete energy. But for the force, we have to rely on the force expression. So we don't take a derivative of the discrete energy directly, but we take the force density from the variational formula, which is given as a geometrical function like h or g and Laplacian and so on. And then given this, we calculate the force directly. Then it doesn't conserve momentum, as you can imagine, because it doesn't take from the Newton law, right?
So
yeah, thank you so much.
Follow Jiayan's question. So when you compute the force from the variational form and does not conserve momentum, is that important for the equilibrium configuration?
It's not really, actually, but to puzzle me is, for most of the shape I get, they are okay. You know, you see here, but for the challenging one, it's very sensitive to tiny details. You know, the triangle, where they are and how they are located. It become, even I don't show here because they become very unstable. You see, scheme C, they have the same expression as scheme D. It's still stable and works. But for scheme D, although the energy is easy to calculate, but for the force, it's so sensitive to the grid or to the mesh. It's easily break down for this very weird shape of vesicle. But look at B in contrast. I gave only a few triangles. It runs very happily.
Yeah, I saw that. Any question? Any other question?
This is Jin. I have a question. Yeah, actually, it's a nice talk. I have a question on the last part of your talk. Using your model, you get different cell shapes, like the echinocyte shapes for the red blood cells. I'm wondering whether these shapes are in stress-free state or not.
So these have the same stress-free shape. So when I was looking into this field, I was always confused when people talk about stress-free shape. But stress-free shape means only the membrane skeleton. Doesn't mean the whole RBC, right? RBC has two components.
Yes.
Stress-free shape only means this equation's stress-free shape. Where? Here, the second equation.
For the cytoskeleton part.
Right. So they are exactly the same for all the SDE sequence. The only difference for this sequence is the delta A0 from the lipid bilayer part, actually.
Mm-hmm.
So nothing to do with membrane skeleton, because you can combine the H0 and delta A0 to have one parameter. They have the same dimension in the end. So this single parameter connect the physiology or chemistry with mechanics. By changing this single parameter, you get different equilibrium shape of a red blood cell. And for most of the people, when we study healthy biconcave RBC, right, we only have one value of this reference state.
Okay.
But this model can do all of them.
Yeah. Then I have another question. So for the total free energy is in the minimum not, because you include the lipid bilayer part and the cytoskeleton part.
So then that means if I have this these shapes at equilibrium, that's the total energy is the minimum.
Okay.
So
yeah,
either of them may not be at the minimum, right? Combined together is the minimum, because you have two portion of energy. That's the membrane skeleton plus the lipid bilayer.
Makes sense. Thank you.
Yeah.
Yeah, I noticed that we have an audience from all around the world. We have people from Germany. We have people from, I saw Eagle from the Switzerland, and I also see Salah from France. So actually, we have this platform. We provide the opportunity to connect the entire world. It's very good. So any other question? So if you have a question, you can feel free to unmute yourself and ask a question to Dr. Bian directly, okay? So then I will ask one question about the breakup of the membrane. I noticed that your configuration can generate very narrow neck geometry, and because the model is based on continuum-based model, you do not allow the membrane break up, right? Is that possible? Because in reality, if the curvature is so big, and the surface energy can be, the bending energy can be so large, and to generate the breakup of the membrane. I'm not sure if there is any guidance to indicate what's the maximum curvature you can model, or if that is possible to induce some breakup of the membrane in this kind of model.
I see, Zen. I think your question maybe I cannot answer directly, but because I can understand in two ways, whether physically this membrane already break up, and secondly, whether numerically it has already, non-machine number, so to say, right? Like infinite. Yeah. So physically, I would say at this parameter, it should break up. So if we really want to model this thing, we have to introduce an ad hoc mechanism, saying that when the thickness of the neck becomes so narrow, below, let's say 10 micron, we have to break up it, make it two sphere topology instead of one. So that's physically. So in this parameter range, it should break up. And secondly, numerically, I think somehow, although I didn't do the analysis, this scheme B, it has this next feature. Somehow it has a cap or maximum of the numerical value. It doesn't go beyond infinity. So it has regulated itself. So which is coincident, of course. It's not by design. It doesn't go to infinite number. Although we have two triangles, it's very big curvature. Somehow it has this regularized property by itself, coincidentally.
Okay, I understand. Because the scheme itself will regulate the energy.
Yes, So
Okay,
I leave it run for a long time. It doesn't break up. It stays with two triangle connected to two spheres. It's very surprising.
Yeah, but if you do not have any scheme to make sure you can handle the breakup mechanism, then maybe if your member break up, your simulation will blow up, right?
Right, of course. That's exactly what happened to scheme D actually. It always blow up when you have this nasty shape.
Okay. Okay, then we will end here today. So if you have any additional question, you can contact Dr. Bian directly. So Dr. Xin Bian is also a organizer of the CFSM seminar. So his contact information is on our website. So you can send him email and communicate directly. Okay. So we were end here today. Thank you.
Thank you. Thank you for your attention.